Hey Tony, this is Ian Ward.
And this is Aaron Gavin.
Gloria Felix. Vanessa Molina. Tiffany Ayala.
And I'm Javier Valdez.
This is All Is Good!
And we're experimenting with microwaves.
Hey Tony, like we said, today we're going to be experimenting with some microwaves, or a microwave, excuse me. How a microwave works, essentially, it emits microwaves at a certain frequency. Most of them are 2.4 gigahertz. These microwaves go through your food, rotating water molecules in there, and that's what actually heats up your food.
Alright, so most microwaves have a 2.45 gigahertz rating written in the back, but this one for some reason doesn't. So what we're going to do is we're going to use marshmallows. We're going to put some marshmallows in there and we're going to find out the frequency.
So we know that velocity is equal to distance over the period. Frequency is equal to 1 over the period. So velocity is equal to distance times frequency. Distance is the wavelength and velocity is the speed of light. So the speed of light is equal to the wavelength times frequency, which in turn equals frequency equals the speed of light over wavelength.
So we're going to determine the frequency by laying marshmallows all over this cardboard. So we're going to lay the marshmallows one marshmallow high, and this whole board will be covered with one marshmallow high like this. And so we put this cardboard with all the marshmallows into the microwave, and we turn the microwave on for a little while. And after a while there will be melted rings of marshmallows and there will be non-melted rings of marshmallows. And basically what that is the constructive and destructive interference of the microwaves. So the melted is the constructive interference and the non-melted is the destructive interference. So once we have these melted rings, then we measure the distance between two melted rings, but we measure all across the board, and each measurement should come up with the same distance, and that is half a wavelength. So from there we can double that and we have the wavelength, and now we can determine the frequency of the microwaves.
Alright, so now to start lining up the marshmallows. Okay, we're finally done. Now let's see those microwaves in action.
The battery's burning out.
Alright, they're getting bigger.
So wait, we stop it when they we stop it like when they get big, and then
Yeah, and then we'll measure it.
okay.
Alright, they're done. Let's check them out.
Yeah.
I'd rather live with... Oh, it smells good. As you can see, most of the hot spots were probably in the end. That's where it was most hot in the microwave. So let's take them out and measure them.
Well, from the experiment, we see that we have 3 hot spots in the microwave. We got one hot spot here, one hot spot there, one hot spot here. And they're about the same distance apart, and which is about 12 centimeters. And we could also see that the constructive interference melted the 3 hot spots, and then the destructive interference didn't melt some of the marshmallows at all. And Going back to the equation we said earlier about wavelength equals the speed of light over the frequency, we can see that this works out at the average wavelength of many microwaves, which is 2.45 times 10 to the 9th seconds, hertz. There you go. Which makes it about 12 centimeters, and that's exactly what we got right here. Right.
Alright, well now that we've experimentally determined the hot spots in the microwave, we have a few other fun things to show you. I'm going to show you how to make a light show with a candle and a match. So first, you gotta light the match. And normally if there's a wick in the candle, you can light it. But the wick in this candle is pretty much burnt out. So we are just going to set the match inside of the candle. And just pop that in the microwave for a few seconds. If it starts.
Cooking.
Ah. Don't know how to use Ian's microwave.
Whoa!
That is so cool.
Oh my god.
Ian, do you like your microwave very much?
That's pretty cool.
Don't do this for more than a few seconds.
Serious.
Hopefully the roof isn't burnt.
Alright.
So we just put this candle in the microwave, and then you saw lights shooting up into the top of the microwave. And so we talked to Tony earlier today, and he told us that when there's plasma and then you have electromagnetic waves going through, there's also there's ionized atoms and then there's electrons. So when the electromagnetic waves are interacting with the electrons are basically traveling up the electromagnetic waves. So when the lights are going up to the roof of the microwave, then that's the electrons traveling along the electromagnetic waves.
Do you remember the good old days before iPods? When we used to put something in CD players called CDs? But what about putting them in the microwave?
That's it. Let's see more.
Do not try this at home, kids.
Alright, so what happened to the CD is that the aluminum on the CD is so thin that the microwaves are the microwaves in the microwave are exciting, and the electrons on it are exciting from the electrons on it, and when they relax again, they give off a light that looks like lightning in the microwave.
Alright, so those 3 experiments were fun. Now let's see what happens if we put them all together.
Whoa!
I was tired. It smells horrible.
I know.
And the microwave's not damaged.
Alright, so today we experimented with things inside of the microwave. We were able to figure out what's the frequency the microwave uses using the marshmallows. We give you a nice little light show using a candle, because it turns into plasma. And we also showed you another light show using a CD, because it excites the electrons in the aluminum. And then we set them all 3 together to give the best show of all.
Alright guys, this is All Is Good, and today we had fun with microwaves. I hope you guys had fun too.
Try it at home. It's safe. Yeah.
Well, we can't be. Yeah, but seriously, We can't be held responsible for this, so please don't sue us.